Hey, how's it going? This is Will Sutherland doing Lab 2 Projectile Motion. So, in this lab, we threw a piece of balled up paper to the ground and modeled the trajectory of that paper using tracker and compared it with glow strip models of the paper under a constant force of gravity and under a non-constant force of gravity and drag. And so the purpose of this was to understand the differences between constant and non-constant forces and how to apply them using coding. So in our models, we found the initial position and velocity using tracker. As you can see here, what we did, we had our meter stick up there. We set our initial position in X to be 0, and then found our Y using our calibration stick. And we tracked the path of the paper using a time step of 1/30th of a second. And so we just found our initial velocities in our X and Y directions by just doing our V average. So change in X over change in T, or change in Y over change in T, between 0.0333 seconds and 0 seconds. So as I just said, our initial conditions, but the velocity, or the mass, of the ball was 0.0045 kilograms. And again, our position was this, our velocity we found there, a time step, 1/30th of a second. So the biggest thing for this model that we had to find was our net force. And so we knew that there was the force of gravity which, in our y component, in our y direction, negative y direction, which is just the mass times the acceleration due to gravity. But there's also our drag force, which is b times v squared, velocity squared, times the direction, so v hat, direction of that velocity. And we know that for any, like any unit vector, so v hat is equal to v over the magnitude of v. So that is all I did here, basically. I found the magnitude of v and the unit vector for v, and then just found vx and vy in those directions using those two. And then plugged it into our formula here in our x and y components, with z being 0 because there was nothing there. So finally, we needed to use our velocity and position update formulas. So initial velocity plus f net over mass of the ball times delta t. Position was just initial position plus the velocity of the ball times delta t, because the velocity of the ball is just v average, and v average and under non-constant forces is just vf. And so we also needed to visualize the errors of velocity and drag and gravity, which I did here. I used a scale of 100 so that, and divided some of them by different numbers, so that way they could all the arrows would be visible to you. And in our axes, it's simply just plugging in what the actual formula for that is, and then the position of where that arrow is placed is just the position of the ball at that spot. So that comes out shown like this, where this green arrow line is the trajectory of our ball, the purple line is our velocity, the cyan line is our the magnitude is our force of gravity, and the orange one is our drag force. So to discuss, the trajectory of the paper we observed in our experiment slowed down more in the x direction than in the y direction. So using b equals 0.001131, the trajectories in the vertical direction match with very little error. However, as you can see here. However, the horizontal trajectories did not, again, as you can see here, implying that there are two separate proportionality constants for the x and y direction. Because if you try to change it so that, change b so that our with drag will match with the observed, then it will change this one so that it does not match. So therefore, there should be two separate ones that if you multiply them, they should both be the same, or both be close. And so this could have been due to something like uneven surface areas along the paper. So where essentially more particles of air would be interacting with the paper horizontally than vertically, causing it to slow down more. So some questions about drag force. Did any of the models predict a terminal velocity? No, but we could find the terminal velocity of the paper. You just need to drop the paper from a very large height, or just a large height, and track when the paper begins to fall at a constant velocity, or a terminal velocity, because that is where the magnitude of the force of gravity is equal to the magnitude of the drag force. And so question 2, imagine if the object were initially thrown straight up with the same initial speed as in this experiment. Would the time the object takes to reach the ground be the same, longer, or shorter than the time it took in the original experiment? It should, in fact, take longer. Under a constant net force due to gravity, it would take the same amount of time, no matter what direction the paper is thrown in. However, with drag force, and that is not the case. We know the drag force is proportional to velocity squared, so that meaning as velocity increases, so too does the drag force, which pushes in the opposite direction from that velocity and the acceleration due to gravity. So as velocity increases and accelerates downward, it's also slowing down inadvertently because the drag force is also increasing in the opposite direction, meaning it will take more time to reach the bottom. So in conclusion, in the presence of air, not in the vacuum, objects in motion experience a drag force that points away from the direction of motion. Drag is a non-constant force that changes with respect to velocity squared, the direction of that velocity, and a proportionality constant b. This is very important to know and to apply to models that predict the motion of objects. Thank you very much.